In your last lesson, you learned a lot about the transformer. The transformer is an example of a specific use for two coils. In lessons prior to the one on transformers, you studied the coil. You learned that as current changes through the coil, the magnetic field around the coil reacts to this change. Your lesson today deals with another electronic component, the capacitor, whose function is almost exactly opposite from the inductor. But between the two, there are certain similarities. The capacitor, like the inductor, temporarily stores energy. However, while the inductor stores energy in its electromagnetic field, the capacitor stores energy in an electrostatic field. An electrostatic field can be defined as a field of force between two electrically charged bodies. This definition gives you an insight as to the construction of a capacitor. The capacitor will appear in many varied shapes and sizes. But regardless of its physical size or shape, you can be sure that it consists of two plates separated by a dielectric. Dielectric is the term applied to the insulating material between the plates of a capacitor, while the plates themselves are of a conductor material. The dielectric could be one of several materials, such as oil, paper, mica, and it could even be air. This capacitor uses air as a dielectric between the plates and is a variable capacitor. The symbol for a variable capacitor is the normal capacitor symbol with an arrow drawn through it, as is shown here. This indicates that the value of the capacitor can be changed. This type of capacitor, with air as the dielectric and with these movable metal plates, is used where you want to tune a circuit. Now, if you've ever looked into a radio, I'm sure you've seen this type of capacitor. Remember, the air dielectric capacitor is constructed of movable metal plates and is used for circuit tuning. Complete number 1 on your response sheet. You should have written movable metal and tuning. Now, if you use such words as variable or adjustable instead of movable, you're still correct. Now complete number 2. Your answer this time should be movable metal plates and circuit tuning. The movable plate capacitor is the most common variable type that's being used. Probably the most common fixed capacitor in use today is the paper dielectric capacitor. The reason it's very common is its low construction cost. Here's how it's constructed. 2 layers of tin foil separated by a layer of paper rolled into a cylindrical shape. After the capacitor is rolled, it's dipped in melted wax so it will retain its shape. This is a very inexpensive capacitor for the job it can do. Now we have two capacitors, the air dielectric we discussed first, and now the paper dielectric, whose construction feature is its cylindrical shape. It is used in most low-cost installations. Now complete statement number 3 in the spaces provided on your response sheet. You should have answered cylindrical shape and low-cost usage. Now do number 4 on your response sheet. Your answer should have been cylindrical shape and low-cost usage. Now, let's move on to another capacitor, and we'll discuss its construction features. This capacitor is usually identified by the fact that it's housed in a round metal can. In other ways, its physical shape is very similar to the cylindrical paper capacitor. It's used when you want a very large capacitance in a fairly small space. The electrolytic capacitor has aluminum plates separated by paper with an extremely thin film of aluminum oxide formed on one of the plates. This is the dielectric, and this is also why it's called an electrolytic. These round metal case capacitors are polarized and can be used in DC circuits only. They cannot be used with AC because a reversal of applied voltage would destroy the dielectric film. For this reason, the terminals are polarized. I mean that one terminal is marked negative and the other is marked positive. The capacitor must be connected according to this polarity marking and used only in a DC circuit. Now we have covered 3 capacitors, the last being the electrolytic, which is housed in a round metal can and provides a large capacitance value and still is comparatively small in size. Remember, it is polarized and must be connected into the circuit properly. Now complete number 5 on your response sheet. You should have completed the statement so it reads like this. Electrolytic capacitors are housed in round metal cans, large capacitance, small in size, and are polarized. Try number 6. Under construction, you should have round metal can and large capacitance, small size, and are polarized under usage. Now, there's one other capacitor in a metal can which we should discuss. This one takes the shape of a square or rectangle. The square or rectangular capacitor uses oil for a dielectric. The oil dielectric capacitor provides all the advantages of the electrolytic type. That is, it has the same large capacitance and is reasonably small in size, and in addition, it has one very important advantage over the electrolytic capacitor. You'll notice that there are no polarity markings on the can. It is not polarized and can be used in both DC and AC circuits. Remember, large capacitors of the electrolytic and oil-filled types are both contained in metal cans. They are both relatively small in size, that is, small for the amount of capacitance they have. The round one is polarized and must be used in accordance with its polarity markings in DC circuits only. The square or rectangular has an oil dielectric and is not polarized. Therefore, it can be used in either DC or AC circuits. Now complete number 7 on your response sheet. You should have completed the statement so that it reads, oil dielectric capacitors are housed in square metal cans, large capacitance, small size, and are not polarized. Now complete number 8. The correct answers are square metal can for construction and large capacitance value, small size, and not polarized for usage. Now let's look at a couple of capacitors that are physically different, but they have the same general usage. These are quite small in size and have a small capacitance. Their greatest advantage over other capacitors is that they are protected from dampness or extreme humidity. Let's refer to them as humidity-proof. The reason they're humidity-proof is that during their manufacture, they're completely encased in a waterproof material. The plates of the mica type are meshed, as indicated here, to cut down on space. Sheets of mica are placed between the plates. The entire assembly is then encased in a plastic and looks like this. The ceramic disc type starts out as two plates with leads attached. Sheets of ceramic material are placed between these plates, and the entire assembly is coated with a plastic material. In both cases, the outside plastic coating acts as a protective covering against humidity. Now we have discussed 5 different capacitors: air, paper, electrolytic, oil, and finally, the ceramic. The ceramic capacitor is wafer or disc-shaped, small in size, and has small capacitance and is humidity-proof. Now complete number 9 on your response sheet. The desired answer in this case is ceramic capacitors are wafer or disc-shaped, small in size, have small capacitance, and are humidity-proof. Any order is okay here. Now try number 10. The construction is wafer or disc shaped, and under usage you should have small size, small capacitance, and humidity proof. Now, you've heard me speak of the various capacitors as having large and small capacitance. When I say large capacitance, I'm saying that it has the capability of creating a large electrostatic field. The electrostatic field results from the charge on the two plates. Now, you recall that the storage of energy in a coil is in the magnetic field. In the capacitor, the energy is stored in the electrostatic field. The ability of a capacitor to store electrons when charged is measured in farads. A 1 farad capacitor connected to a 1-volt battery would have 1 coulomb of electrons on its negative plate. A 1 farad capacitor would be a gigantically large capacitor. You'll never see one. Practical capacitors, the ones that you'll see, will have capacitance values in microfarads or microfarads. Many times it will be necessary for you to complete problems which require converting the micro or micros to a whole farad. Now, this can be done in 2 ways. Here are two values of capacitance. Let's convert these to farads. First, we must answer this question. How much is a microfarad? Well, you should know that micro means 1 million. And it also means that the decimal point must be moved to the left from its original placement. Therefore, I can write this value in this manner. This is the way to express the value, 0.25 microfarads in farads. But you also know how to use the powers of 10, and that's the simplest way to write this number. All you need to do is count the number of places to the right of the decimal point and write the value as I did, using the number of places as the minus power of 10. Now, in this one, we must move the decimal point 12 places to the left because it's in microfarads. You can write it the hard way like this. Or the easy way, using the powers of 10, like this. Either way is correct, but using the powers of 10 is, of course, the easiest. Try this one. Put your answer in space number 11 on your response sheet. Your answer, to be correct, should be one or the other of these, preferably 67 times 10 to the minus 7th power. Now answer number 12 on your response sheet. This answer should be as shown here. And again, the preferred one is 53 times 10 to the minus 8th power. Now convert number 13 to farads. Your answer could be either of these. They're both correct. Now here's one last try at it. I hope that you used the powers of 10 expression. However, if you chose the hard way and got the right answer, well, that's okay too. We've converted a few values of capacitance, and we've discussed large and small capacitances. You're probably wondering what determines the capacitance of a capacitor. This illustration should help you remember the facts which govern this. The area of the plates is factor number 1. The larger the plates, the greater the capacitance. Factor number 2 is dielectric constant, symbolized by the letter K. The greater the K value, the greater the capacitance. The distance between plates is factor number 3. This factor works inversely. The greater the distance between the plates, the smaller the value of capacitance. Now, I'm sure that plate area and distance between plates requires no further explanation. However, I'll give you a better understanding of what is meant by dielectric K. It all starts with air as the standard. Air is given a K value of 1 and is considered the poorest dielectric in use. Other materials that are used for dielectrics cause an increase in the K rating. The higher the K, the better the material insulates and the higher the capacitance. Remember the factors which affect capacitance and how they affect it. The factors are now dielectric K, plate area, and distance between plates. Complete number 15 on your response sheet. The correct answers are dielectric K, area of the plates, and distance between the plates. Any order on these is correct. Now try this one for number 16. Capacitance increases with an increase in dielectric K. Now complete number 17 on your response sheet. Again, you should have said increase. Now complete statement number 18. When plate area increases, the capacitance will also increase. Complete statement number 19 on your response sheet. The correct word is again increases. Now complete number 20. The correct answer is decreases. Now answer number 21. This answer is also decreases. The final area I want to discuss with you is this, the voltage rating of the capacitor. Voltage rating can be defined as the maximum DC voltage that the capacitor can withstand. This is also referred to as the breakdown voltage. Any voltage in excess of the breakdown voltage will electrically puncture the dielectric. This is a fancy way of saying that current arcs through the dielectric and in most cases burns a hole, permanently shorting the capacitor. Now, the three factors which determine the voltage rating of a capacitor are the dielectric K, the distance between plates, and finally, the thickness of the dielectric. When an electrical charge is built up between two bodies, like the plates of a capacitor, there's a tendency for a current to arc between the two bodies. Whether we get an arc or not depends on how far the current has to jump and the insulating quality of the dielectric. The further apart the plates are, the higher the dielectric K, and the thicker the dielectric is, the higher the voltage rating will be. Remember these factors, dielectric K, the distance between the plates, and the thickness of the dielectric. Now try question number 22 on your response sheet. You should have answered dielectric K, distance between the plates, and thickness of the dielectric. These can be in any order. Now complete number 23. Your answers are dielectric K, distance between the plates, and thickness of the dielectric. Once again, these can be in any order. Remember, to explain voltage rating of a capacitor, one would have to say the breakdown voltage. Now, by that, you know that I mean the breakdown of the capacitor will result at this voltage. An example of this is when the insulating effect of the dielectric is overcome and current arcs from one plate to the other. Answer number 24 on your response sheet. Your answer should be breakdown voltage. Now answer number 25. This answer is also the breakdown voltage. Well, this completes the first of 2 lessons on capacitors. Your next lesson deals with how the capacitor reacts in both DC and AC circuits.